Somewhere right now, 4 people are travelling at roughly 25,000 miles per hour inside a capsule the size of a large SUV, with a heat shield that spooled and cracked on its only test flight and was never replaced. NASA ran the numbers, held the meetings and said, acceptable. 1 in 30 chance of losing the crew. That is the internal threshold. 1 in 30. Knowing that, the crew still got in. And honestly, once you hear everything they actually knew going in, the solar storms, the 45-minute blackout behind the moon, the parachutes, the number that surprises you will not be the risk. It will be the courage. Before we begin, if you are new and enjoy what I do here, make sure to hit like and subscribe so that you don't miss anything as this story develops. And I do not want to sound alarming, but by the time we're done, the worst case scenarios are going to feel deeply unsettling. Now get cozy and let's ease into it. Part 1. The gamble has already started. Right now, 4 human beings are sitting inside a capsule roughly the size of a large SUV, travelling at speeds that would take you from Nairobi to London in under 4 minutes, farther from Earth than any person has been since December 1972. And the heat shield protecting them from incineration on the way home already cracked the last time it was used. Let that land for a second. NASA knew about it. The engineers knew about it. The astronauts knew about it. And everyone involved looked at that information, ran the numbers, held the meetings and said, we accept this. We fly. That decision is what Artemis II actually is. Not a mission to the moon, not a celebration of exploration, not a press release about the future of humanity. It is a formal, documented, institutional acceptance of uncertainty at a scale that most people have never had to think about. And if you want to understand what these 4 astronauts are genuinely facing out there right now, you have to start not at the launch pad, not at the countdown clock, but at the moment a group of engineers looked at a broken heat shield and decided the answer was not to fix it, but to change the angle of approach. Because that choice, made quietly in a conference room somewhere at Johnson Space Center, is the defining engineering philosophy of this entire mission. And it has consequences that stack on top of each other like geological layers, each one thin enough to seem manageable on its own, each one sitting on top of the last until you start to see the actual shape of the risk these people accepted. Not the polished version, not the press conference version, the real shape of it. So let us go through it. All of it. From the heat shield that should have grounded everything, to the 45-minute window behind the moon where no one on Earth can hear them, to the scenario that physicists actually lose sleep over, which, spoiler, is not the explosion. The explosion is not the thing that should worry you. The thing that should worry you is a successful mission. But we are getting ahead of ourselves, and I want to be careful not to rush this, because the details matter enormously here. The details are where the actual story lives. Start with what we know. Artemis II is a crewed lunar flyby, the first time humans have travelled beyond low Earth orbit since Apollo 17 in December 1972, 53 years ago. The crew of 4, Reed Wiseman, Victor Glover, Christina Koch, and Canadian astronaut Jeremy Hansen, are flying what NASA calls a lunar free return trajectory. That phrase sounds reassuring. Free return. Like there is a safety net built into the physics of the thing, and in a very narrow, very specific, very physics-dependent sense there is. If nothing catastrophic happens, the geometry of the moon's gravity and Earth's gravity will arc the spacecraft back toward home without requiring a propulsion burn. Gravity does the work. You point the spacecraft correctly, execute the burns at the right moments, and the orbital mechanics of the Earth-Moon system guide you home like a river finding the sea. But the word free is doing a lot of lifting in that phrase, because free return only works if everything else works first. The trajectory has to be set correctly. The burns have to execute on time and at the correct thrust levels. The spacecraft has to remain functional throughout the transit. And critically, the crew has to survive a re-entry at roughly 25,000 miles per hour, 40,000 kilometers per hour, through an atmosphere that will heat the outer surface of their capsule to temperatures around 5,000 degrees Fahrenheit. To put that number somewhere useful, 5,000 degrees Fahrenheit is approximately half the surface temperature of the Sun. It is hot enough to melt steel in seconds. It is hot enough that the air itself around the capsule ionizes. The molecules of nitrogen and oxygen in the upper atmosphere get so energetically disrupted by the capsule's passage that they lose electrons and become plasma. The capsule is effectively surrounded by a sheath of star stuff for several minutes during re-entry, and the only thing standing between the crew and that is the heat shield, the one that cracked. This is where the story actually begins, and it begins not with a dramatic failure but with something more insidious, an anomaly discovered after the fact in the quiet forensic examination that follows a test flight. When Artemis I flew in November 2022, an uncrewed test of the full Orion spacecraft and Space Launch System stack, it was considered a success by every public metric available. The capsule splashed down in the Pacific Ocean, the parachutes deployed on schedule, the spacecraft executed its lunar flyby correctly. NASA held a press conference and talked about milestones and new eras of exploration, and by the standards of an uncrewed test flight, all of that was accurate. The mission did what it was supposed to do. The data was collected, the hardware was recovered. But in the weeks and months that followed, as engineers went through the recovered spacecraft with the kind of forensic attention you only apply to hardware that is about to carry human beings, they found something that was not supposed to be there. The heat shield had eroded unevenly, not dramatically, not in a way that would have been obvious from the outside or from the telemetry data during the mission itself. But when you looked at the physical surface of the recovered heat shield up close, you could see it. There were pockets of erosion that went deeper than the thermal models had predicted. The ablative material, a substance called AV coat, which is specifically engineered to burn away in a controlled, predictable manner during re-entry, absorbing and carrying away heat rather than conducting it into the capsule structure, had not behaved the way the simulation said it would. More specifically, there was evidence of internal gas entrapment. Bubbles of gas had built up inside the AV coat material during the manufacturing process, or the re-entry thermal cycle, and those bubbles had created localized pressure points within the material. That internal pressure had caused cracking, and that cracking had caused what engineers call spallation, pieces of the heat shield material physically breaking off and separating from the surface during the highest thermal stress moment of the entire mission. Take a moment with what that means physically. During re-entry, the heat shield is the forward-facing surface of the capsule, the part that hits the atmosphere first. It is doing its job by burning. That is intentional. AV coat is designed to ablate, to sacrifice itself through a controlled burning process that carries thermal energy away from the capsule rather than into it. The outer layers burn, new layers are exposed. Those burn too. It is a thermal sacrificial system, elegant in its simplicity, and it has worked on every crewed capsule re-entry in the history of American spaceflight. But spallation is not controlled burning. Spallation is uncontrolled fracture. It is pieces of material departing the heat shield surface, not as a result of the designed ablation process, but as a result of internal mechanical failure. And those pieces, once separated, do not simply float away harmlessly. They are carried by the hypersonic flow around the capsule. Depending on their trajectory, they can impact other surfaces of the spacecraft. They can travel backward in the aerodynamic wake toward the parachute compartment, the same compartment that contains the only system capable of slowing the capsule from terminal velocity to survivable splashdown speed. If debris from a spalling heat shield impacts and damages a parachute before deployment, the failure cascade from that single event has no recovery path. So the question that had to be answered was simple in its phrasing and genuinely difficult in its answer. The question was, do we understand why this happened well enough to predict, with sufficient confidence, that it will not kill anyone on the crewed mission? The answer NASA arrived at was mostly. And mostly in human spaceflight is the closest thing to certainty that exists. Not because the engineers are cavalier or the risk assessors are sloppy, but because the system is genuinely, fundamentally complex in ways that resist complete characterization. You can build the best models available with the best data available and still be operating in a space where the honest answer to "are we sure?" is "we are as sure as the current state of human knowledge allows us to be," which is not the same as completely sure. Here is what they found when they dug into the AV coat anomaly. The heat shield on Orion is fundamentally different from anything that flew during the Apollo program, and the difference is not just one of scale. Orion is roughly twice the mass of the Apollo command module, a significantly larger vehicle carrying more equipment, designed for longer mission durations with more capable systems. The heat shield is correspondingly larger, and when you scale up an ablative heat shield, you're not simply making the same system bigger. You're entering a thermal regime that has never been physically tested at that scale, under actual re-entry conditions. The physics of how heat moves through ablative materials, how internal pressure builds during the heating cycle, how the material responds to the specific combination of temperature gradient and mechanical stress during skip re-entry, all of that behaves differently at Orion scale than it did at Apollo scale, and the models that predicted the behavior were built on data from a different size regime. The models predicted behavior. The models were wrong. Not catastrophically wrong. The capsule came back. The heat shield did its job in the aggregate, but wrong in ways that were consequential enough to notice and consequential enough to worry about for a crewed mission, even if, according to NASA's formal risk assessment, not consequential enough to require a full hardware redesign before flying humans. That phrase, "not consequential enough to require redesign," is one of those engineering determinations that sounds entirely reasonable inside a risk framework built on probability distributions and fault tree analysis, and sounds genuinely unsettling when you say it out loud to someone who has not spent years working inside that framework. The reason it sounds unsettling is not because the engineers are wrong to use it. It is because it is accurate to both interpretations simultaneously. Inside the framework, it means the probability of mission failure attributable to this specific failure mode falls within the accepted range. Outside the framework, it means we are flying humans on hardware with a known failure mode that we have chosen not to fix. Both of those things are true at the same time, and that tension is the thing you have to sit with if you want to understand what Artemis II actually represents. Because this is the point where the Apollo comparison becomes genuinely important, and not in the way that most Apollo comparisons get made. The usual framing is nostalgia, the heroism of the Apollo era, the audacity of the achievement, the romance of a simpler time in human spaceflight. That framing is not wrong exactly, but it misses the thing that matters most for understanding Artemis. Apollo operated under a philosophy that could be summarized as bravery over uncertainty. The engineers and astronauts of that era knew, with remarkable clarity, that the systems they were building and flying were incomplete. They knew the margins were narrow. They knew that the rockets were flying on the edge of what the metallurgy and the guidance computers and the life support systems of the 1960s could support. They accepted that danger not because they had modelled it into an acceptable probability range, but because they believed the mission was worth the risk, and because their response to any gap in the system was to fill it, with hardware, with redundancy, with ingenuity, with the kind of engineering culture that pulled off Apollo 13's improvised return on 4 days' notice. When something failed in the Apollo program, you redesigned it. When a gap appeared in the system's capability, you identified it and you filled it. The culture was hardware first. The assumption was that unknown risks were best addressed by reducing the unknowns, not by modelling them. Artemis operates under a genuinely different philosophy, and it is worth naming it precisely because it is not a lesser philosophy. It is a more sophisticated one, in certain respects, and a more honest one about the limits of what engineering can actually achieve. The philosophy is called bounded uncertainty. The core idea is that in a system of sufficient complexity, and a crewed spacecraft transiting to the moon and back is certainly a system of sufficient complexity. You cannot eliminate risk. You can only characterize it. You can define the boundaries of what you do not know. You can assign probability distributions to failure modes. You can build confidence intervals around your predictions. And then you can make a formal documented determination about whether the probability of crew survival across the full mission profile sits inside the range that has been defined as acceptable. NASA's internal threshold for crew loss probability on Artemis II has been described in various documents as approximately 1 chance in 30. 1 in 30. That number needs context before it can mean anything. For comparison, Apollo 13, the mission we most associate with near-catastrophic failure and remarkable survival, had a retrospectively estimated crew loss probability of approximately 1 in 10 by some analyses. And we consider Apollo 13 a triumph of engineering because everyone came home. So when you hear 1 in 30 and think that sounds low, you are right that it is lower than 1 in 10. But you are also sitting with the fact that 1 in 30 means that in a hypothetical universe, where you flew Artemis 230 times with 30 different crews, the statistical expectation is that one of those missions does not bring its crew home. That is not a comfortable number. It is, by the standards of modern spaceflight risk assessment, an acceptable number. But those two things, uncomfortable and acceptable, can both be true, and the people who made that determination know it. Which brings us back, inevitably, to the heat shield. Because NASA's response to the Avicoat anomaly was not to replace the heat shield. The decision was made after extensive analysis and review that a heat shield redesign would introduce delays measured in years, delays that would push Artemis II well beyond its planned launch window, affect the entire downstream mission schedule for the Artemis program, and consume resources that the program did not have available. Instead, engineers chose a different path. They modified the re-entry trajectory. Specifically, they adjusted the descent angle to make it slightly steeper. The logic is straightforward. The problem with the heat shield was gas entrapment leading to internal cracking leading to spallation, and the behaviour was amplified by the duration and nature of the thermal loading during re-entry. A steeper descent angle means the capsule gets through the peak heating phase faster, less time at maximum thermal stress, lower cumulative heat absorption during the most critical portion of the re-entry profile, reduced probability of the gas entrapment and spallation behaviour repeating at levels that could threaten the mission. It is an elegant solution in exactly the way that engineering solutions often are elegant. It addresses the observable symptom with precision and without touching the underlying cause. The underlying cause is a heat shield material whose behaviour at Orion scale is not fully characterised. The trajectory modification does not change that. What it does is reduce the exposure of the incompletely characterised material to the conditions that revealed its incompleteness. You're not fixing the problem, you're narrowing the window during which the problem can express itself in dangerous ways. And here is the part that matters, the part that reveals the deeper logic of how risk works in interconnected systems. A steeper descent angle reduces the duration of peak thermal exposure, but it also increases the intensity of thermal loading during the window that remains. You're compressing the same thermal event into a shorter time frame, which means the peak stress on the heat shield material, in terms of rate of temperature change, in terms of instantaneous heating flux, is higher than it would have been on the original trajectory. You have traded duration of exposure for intensity of exposure. The total thermal budget may be similar or even lower, but the peak stress the material experiences in any given moment is greater. You have moved the risk, you have not removed it. And that distinction between moving risk and removing it is the single most important concept for understanding everything else about this mission, because it applies to every engineering decision that follows, every backup plan, every workaround, every compensating adjustment in the Artemis II mission profile is a version of that same trade. In a system this complex, you are never solving problems cleanly. You are redistributing consequences across a web of interconnected variables, and hoping, with as much mathematical rigour as you can bring to the hope, that the redistribution lands in a configuration where nothing catastrophic happens to coincide with anything else catastrophic. The heat shield bolts also partially melted during Artemis I, by the way. That detail received considerably less public attention than the spallation anomaly, partly because it is more technically obscure and partly because the language around it in the official reports was carefully measured. But it matters. The heat shield on Orion is not a single monolithic component. It is an assembly, and like all assemblies, it has fasteners. Bolts that hold elements of the heat shield structure in relationship with each other and with the capsule body during the thermal extremes of re-entry. On Artemis I, some of those bolts experienced thermal loading that exceeded their design specification. They did not fail completely, but they experienced conditions beyond what they were designed for, and in the context of a heat shield already exhibiting anomalous behavior, additional stress on the fastening system introduces additional failure pathways into an already complex picture. If the bolts fail at the wrong moment, during the critical phase of re-entry, when the heat shield needs to remain structurally integrated with the capsule body, the failure does not stay local. It cascades. A compromised fastening system can introduce mechanical instability into the heat shield assembly. Mechanical instability under hypersonic aerodynamic loading can propagate, and a heat shield that begins to separate from the capsule structure during peak re-entry heating is not a recoverable situation. So let us inventory what we have, because I want you to hold this clearly before we move forward. You have a heat shield whose ablative material demonstrated anomalous spallation behavior during its only test flight. You have a fastening system that experienced thermal conditions beyond design specification during the same test flight. You have a trajectory modification that was implemented to compensate for the heat shield anomaly, which successfully reduces the duration of peak thermal exposure, but increases the instantaneous peak stress on the same material. And you have a crew of 4 human beings sitting inside a spacecraft that is, by the formal determination of the most rigorous aerospace engineers on the planet, within acceptable risk parameters. Every one of those things is true simultaneously. And the question that should be sitting at the back of your mind right now, not as panic, but as the right kind of intellectual discomfort, is this. At what point does a managed risk become an invisible one? At what point does the act of quantifying uncertainty, of assigning it probability values and confidence intervals, create an illusion of control over something that is ultimately outside the reach of human control? Because here is the thing about modelling uncertainty. The model is only as good as the data it is built on, and the data for Orion's heat shield behavior at lunar return re-entry conditions consists, in its entirety, of one data point, one flight, one recovered heat shield. The spallation that occurred was outside the model's predictions, which means the model was wrong, which means the new model, the one that says the trajectory modification brings the risk inside acceptable parameters, is an updated model, a better model, a model informed by the anomaly it is trying to account for. But it is still a model, and the only way to fully validate a model of this kind is to fly the mission and see what happens. They are flying the mission right now. The validation is in progress. We will come back to the question of what managed risk looks like when it becomes invisible, because it is going to matter for every section that follows. But the heat shield, as strange as it sounds, is actually one of the more straightforward risks on this mission. There are systems on Artemis II whose failure modes are stranger, more paradoxical, and in some ways more philosophically troubling than a cracking ablative material. The next one involves a piece of equipment sitting at the very tip of the rocket, generating more thrust than 4 fully loaded jumbo jets. That is simultaneously the crew's best chance of surviving a catastrophic launch failure, and under specific conditions, a potential pathway to a completely different kind of catastrophe. The thing about safety systems, it turns out, is that they do not make you safe. They change the shape of the danger, and once you understand that, the entire architecture of a human spaceflight mission starts to look very different than it does in the press releases. Part 2. Systems that can fail without warning. There is a system sitting at the tip of the Orion spacecraft that generates roughly 400,000 pounds of thrust in under 3 seconds. It is called the Launch Abort System, and its entire purpose is to rip the crew capsule away from an exploding rocket faster than a human being can consciously process that an explosion is happening. 400,000 pounds of thrust. Let me give you that number in a way that actually means something, because raw figures without context are just noise. A commercial Boeing 747, the big one, the one that carries 400 passengers across oceans, produces roughly 240,000 pounds of thrust across all 4 of its engines simultaneously at maximum takeoff power. The launch abort system produces nearly double that from a single solid rocket motor that is smaller than a school bus. A single motor. Shorter than the distance from one end of a city bus to the other, generating twice the thrust of one of the most powerful commercial aircraft ever built. And it has to do all of that in a time window measured not in seconds, but in fractions of seconds. Because at the moment of a catastrophic booster failure, at the moment the Space Launch System, which stands 98 meters tall and weighs approximately 2.6 million kilograms fully fueled, begins to structurally fail, the crew has approximately the same amount of time to escape as it takes you to blink. Maybe less. The system cannot wait for a human decision. It cannot wait for a flight controller in Houston to assess the telemetry and press a button. By the time any human being in the loop has consciously registered that something is wrong, the window for a successful abort has already opened and may already be closing. So the launch abort system is automated. It monitors booster performance through a set of sensors and detection algorithms, and if those sensors register a signature consistent with catastrophic failure, the system fires. No human in the loop, no confirmation request. The decision is made by software in milliseconds, and the crew is pulled away from the exploding vehicle at accelerations that can reach 15 times the force of gravity. 15 G. For a brief reference point, fighter pilots in high-performance aircraft typically experience somewhere between 7 and 9 G during extreme maneuvers, and they train for years to maintain consciousness at those levels. The launch abort system subjects the crew to 15 G, involuntarily, with no warm-up, for the duration of the abort sequence. The system is genuinely impressive. It has been tested. It has been validated across a range of conditions. The engineering behind it represents decades of accumulated knowledge about what it takes to save a human crew from the most violent failure mode in rocketry. And it contains within its design a class of failure modes that did not exist before the system was built. This is one of the more counterintuitive truths of complex safety engineering, and it shows up everywhere once you know to look for it. Safety systems do not reduce the total number of ways a mission can fail. They change the distribution of failure modes. They close some failure pathways and, by the very act of existing as additional complex hardware in the system, open others. The launch abort system is a near-perfect illustration of this principle, and working through its failure space is worth doing carefully because it says something important about the nature of safety itself. Consider the full picture. If the launch abort system triggers correctly during an actual booster failure, the crew survives. The spacecraft is destroyed, the mission is lost, but the 4 people inside the capsule are alive. That is the intended scenario, the one the system was designed for, and the system is quite good at achieving it. Call that outcome 1. But the system can also trigger falsely. A sensor malfunction, a software error in the detection algorithm, an unexpected vibration signature from a perfectly functional booster that happens to match the frequency profile the detection logic associates with structural failure. In any of these cases, the system fires when it should not. The crew is pulled away from a rocket that was working. The abort sequence executes. The spacecraft is gone, destroyed or unrecoverable, but the crew is alive. That is outcome 2. It is bad. The mission is over. But in the hierarchy of bad outcomes, crew alive, mission failed sits at the acceptable end of the spectrum, so we categorize it as a success condition and move on. Outcome 3 is the one that does not move on. The launch abort system fails to trigger during an actual catastrophic event. The sensors miss it, or the detection algorithm does not recognize the signature, or there is a hardware failure in the abort motor ignition system at the moment it is needed most. The crew remains inside a vehicle that is structurally failing. The abort window, roughly the first 120 seconds of flight, the period before the spacecraft reaches an altitude and velocity profile where the launch abort system is no longer the primary escape mechanism, closes, and the crew is inside an exploding vehicle with no path to survival. That scenario is genuinely terrible, but it is, in a certain mechanical sense, straightforward. The safety system failed to perform its designed function. The failure mode is clear even if the outcome is catastrophic. Outcome 4 is the one that lives in the more philosophically uncomfortable corners of the engineering trade space. The launch abort system fires correctly. It detects a real failure, or a sufficiently compelling false positive, and it executes. The abort motor ignites. 400,000 pounds of thrust pull the crew capsule away from the failing vehicle at 15 G. The capsule reaches its peak altitude in the abort trajectory. And then the jettison motor, the secondary motor, designed to separate the abort tower from the crew capsule so that the parachutes can deploy, fails to fire. The abort tower remains attached to the capsule. It is sitting directly above the parachute compartment. The parachutes are packed into a space that is now physically blocked by a rocket motor assembly that was supposed to be gone by now. The parachutes cannot deploy through a solid rocket motor. The crew has successfully escaped the exploding booster. The crew is now in a capsule falling toward Earth with no functional parachute system. The launch abort system saved them from the explosion and delivered them to a different unsurvivable outcome. None of these 4 scenarios are likely. Each of them sits within what engineers describe as acceptable probability ranges, individually. The point is not to suggest that the launch abort system is poorly designed or inadequately validated. It is neither of those things. The point is something more subtle and more important. When you build a safety system, you are not making the mission safer in an absolute sense. You're making it safer in a probabilistic sense, within the specific failure domain the system was designed to address, while simultaneously introducing new failure pathways that would not exist if the system were not there. Redundancy improves survival probability in specific, defined, anticipated failure scenarios. It also expands the total complexity of the system, and complexity is where unexpected failures live. Not in the failure modes that were anticipated and designed around. Those get tested and validated and refined. In the failure modes that emerge from the interactions between components, from the edge cases that did not appear in the design simulations, from the scenarios that no one thought to model because they sit outside the envelope of what was imagined. Apollo understood this, or came to understand it through painful experience. The launch escape system on Apollo capsules went through multiple significant design iterations, specifically because early versions created failure modes that the original design had not anticipated. Each iteration addressed the previously discovered failure modes, and, in the nature of these things, introduced new ones that required subsequent iterations. The history of spaceflight safety systems is, in large part, a history of iterative discovery of the ways that safety systems can themselves become failure pathways. Artemis is flying with the most capable, most rigorously tested launch abort system ever built for a crewed spacecraft, which means it is also flying with the most complex set of abort system-specific failure modes ever incorporated into a crewed mission. Those 2 facts are not in contradiction. They are the same fact viewed from different angles. Now, once you clear the launch phase, once the first 120 seconds of flight are behind you, once the launch abort system has been jettisoned and the spacecraft is on its way uphill toward the trajectory that will send it around the moon, the nature of the risk changes completely. The violent, explosive, instantaneous failure modes of the launch phase give way to something different, something slower, something in some ways more insidious, because it is not the kind of danger that announces itself with fire and noise. It is the kind of danger that announces itself with silence. There is no lifeboat on Artemis II. Sit with that for a moment, because I think it is genuinely underappreciated in the public discussion of this mission. We have spent the better part of the last 25 years operating the International Space Station, and in that time, the presence of a rescue vehicle has become so normalized as part of the crude spaceflight architecture that its absence registers almost as an oversight rather than a deliberate design reality. At any given moment on the space station, there is at least one Soyuz capsule or Crew Dragon spacecraft docked to the structure, ready to undock and return the crew to Earth in an emergency. The transit time is hours. The capability is real. It is not a perfect lifeboat. There are failure modes on the station that do not give you the hours you would need, but it exists as hardware, as a physical object with a defined emergency function, and its presence is part of the fundamental operational psychology of being on the station. You know it is there. The crew knows it is there. Mission Control knows it is there. Apollo 13 had a lifeboat too, though it was never designed to be one. The lunar module, that angular, improbable-looking vehicle with its spindly legs and its gold foil thermal blankets, was built to land on the Moon and take 2 astronauts back up to the command module waiting in orbit. It was not built to be a survival vehicle for 3 people on a 4-day emergency return from the Moon. Its carbon dioxide scrubbing system was not sized for 3 people. Its power budget was not designed for the extended operation that the emergency required. Its guidance system was not configured for the burns that needed to happen to get the crew home. None of that mattered in the end because it was there, because it existed, because the mission architecture had included a second vehicle with its own independent power systems and its own independent propulsion and its own independent life support. And when the service module's oxygen tank exploded and the command module became uninhabitable, the crew had somewhere else to go. They crawled through the tunnel between vehicles. They improvised carbon dioxide scrubbers out of plastic bags and cardboard and tape. They powered down every non-essential system to conserve the battery power they would need for re-entry, and they came home. The lunar module was not supposed to be a lifeboat. It became one because it was there. Artemis II does not have a second vehicle. There is no tunnel to crawl through. There is no backup power system in a separate hull. There is no redundant propulsion sitting on a different spacecraft that can be pressed into emergency service. There is one spacecraft, 4 astronauts, and a trajectory defined by the laws of orbital mechanics. The free return trajectory provides what NASA describes as a passive safety mechanism, and it is important to understand both what that means and what it does not mean. If the service module's main propulsion system fails after the translunar injection burn, the burn that commits the spacecraft to its lunar trajectory, the free return geometry means that the spacecraft will continue around the Moon and curve back toward Earth without any additional thrust being required. You do not need engines to come home if the trajectory is set correctly. Gravity does the work. Isaac Newton, working in the 17th century, described the mathematics that make this possible, and those mathematics are as reliable as anything in physics. In that specific sense, the free return trajectory is a genuinely elegant safety feature. But the free return trajectory is not a rescue system. It is a return mechanism, and the distinction matters enormously in practice. A rescue system adapts to your situation. It gives you options. It allows mission control and the crew to assess what has gone wrong and choose from multiple response pathways. A return mechanism does none of that. It does one thing, it brings the spacecraft back toward Earth, and it does that one thing regardless of whether the spacecraft is in a condition to survive re-entry when it gets there. If the heat shield has been damaged, if the parachute system has a fault, if the power systems have degraded to the point where the guidance computers cannot execute the entry sequence correctly, the free return trajectory brings you back to Earth in all of those scenarios. It does not help you survive arrival. This is what it means precisely to say that Artemis II replaces rescue capability with deterministic orbital mechanics. After the translunar injection burn, physics is not a backup system. Physics is the only system, and physics, unlike a Soyuz capsule or a lunar module, cannot be upgraded mid-mission. It cannot be rebooted when it is not working as expected. It cannot be called in from mission control when the situation changes. It is fixed. It is the consequence of decisions made before launch, committed to trajectory geometry, and thereafter completely outside the reach of human intervention. The European Space Agency built the service module that provides propulsion, oxygen, power, and thermal regulation for the Orion spacecraft. ESA's engineering is, by every credible measure, excellent. The service module has been through extensive ground testing and was validated by the Artemis I flight. None of what follows is a criticism of the hardware or the people who built it. What it is an observation about architecture. The service module is a single consolidated unit, providing multiple critical functions that, on Apollo, were distributed across two separate vehicles with independent systems. The service module's 4 AJ-10 derivative engines provide the thrust for every significant burn of the mission, the translunar injection, the course corrections, the critical return burns. Its solar arrays generate essentially all of the electrical power the spacecraft consumes beyond the battery reserves. Its thermal control system regulates the temperature environment that keeps the crew alive and the electronics functional. Its tanks hold the oxygen that supplements the cabin atmosphere. In systems engineering, this architecture is called functional consolidation, and it has real advantages. A consolidated system is lighter than a redundant system performing the same functions. It is simpler to operate, in the sense that there are fewer interfaces between subsystems. It is easier to validate because the integration test scope is narrower. For a mission profile like Artemis II, a multi-day flyby with a defined trajectory, and a relatively constrained operational envelope, functional consolidation makes sense as a design choice. The trade is failure tolerance. On a consolidated system, a failure in any critical function does not stay local. It propagates. A propulsion failure is not just a propulsion failure, it is a trajectory failure, because the burns that define the return path cannot execute. A power failure is not just a power failure, it is a life support failure, a guidance failure, a communications failure, because all of those systems draw from the same power source. A thermal control failure compounds into every other system, because electronics that overheat fail, and failing electronics take other systems with them. Apollo's architecture was almost extravagant in its redundancy by comparison. 2 vehicles, each with independent power. Multiple redundant guidance computers, fuel cells and batteries. Systems designed to continue operating after losing significant portions of their capacity. The mass cost was real. Apollo was a heavy, complex, expensive system by any measure. But the failure tolerance was correspondingly generous. You could lose quite a lot of Apollo and still have a path home. Apollo 13 demonstrated that in the most vivid possible way. Artemis II is a leaner, more efficient, in many technical respects more capable spacecraft than Apollo. Its computers are incomparably more powerful, its sensors are more precise, its communication systems operate at bandwidths that Apollo's technology could not have supported. But it is less modular in the specific sense that matters most when things go wrong unexpectedly. The failure modes that Artemis II handles least gracefully are not the catastrophic, instantaneous ones, the explosion, the sudden hull breach, but the slow, compounding systemic ones. A propulsion system delivering 92% of nominal thrust instead of 100%. A power system losing capacity gradually over the mission duration. A thermal anomaly that reads within tolerance on day 1 and outside tolerance on day 3. These are the scenarios that a consolidated single-vehicle architecture is worst positioned to manage, because each one, as it develops, reduces the options available for managing the ones that follow. And these are also, by a meaningful measure, the scenarios most likely to be undetectable from outside. Once Artemis II is beyond low Earth orbit, there is no visual inspection possible. There is no spacewalk to examine a suspect component. There is no visiting vehicle to deliver a replacement part or provide an independent power source. Mission Control's visibility into the spacecraft's condition is entirely dependent on the telemetry the spacecraft itself transmits, which means a failure that affects the telemetry system simultaneously affects Mission Control's ability to understand what is happening. Which brings us to something that no amount of engineering redundancy, no amount of backup systems, no amount of careful mission planning can fully address. It is not a system failure. It is not a component anomaly. It is a feature of the mission's geometry, built into the orbital mechanics of flying past the moon, and it has a name that sounds almost mundane until you think about what it actually means. For roughly 45 minutes during the Artemis II mission, the moon will be directly between the crew and Earth. Every radio signal that Mission Control sends to the spacecraft travels in a straight line at the speed of light. Every telemetry signal the spacecraft sends back travels the same way. Radio waves do not bend around the moon. They do not diffuse around its edges. The moon is 3,474 kilometers in diameter, with no atmosphere to scatter signals around its limb, and when the spacecraft passes behind it, the electromagnetic connection between the crew and every human being on Earth is physically interrupted. Not degraded, not weakened, interrupted, gone. For 45 minutes, Mission Control cannot hear them, cannot see their telemetry, cannot send commands, cannot warn them, cannot help them. The most sophisticated ground support infrastructure in human history becomes, for 45 minutes, a collection of very expensive antennas pointing at a rock, and during those 45 minutes, the crew of Artemis II will not be resting. They will be executing mission activities, critical ones, navigation assessments, system checks, potentially burn preparations. If anything goes wrong during that window, any anomaly, any system alert, any unexpected behavior in any of the consolidated service module functions we just discussed, Mission Control will not know about it until the spacecraft emerges from behind the moon and telemetry resumes. 45 minutes is a very long time for a problem to develop undetected on a spacecraft, with no lifeboat and a heat shield whose behavior at the edge of its thermal envelope is, by the honest assessment of the people who built it, not completely characterized. But here is the thing. The communication blackout is actually the part of the far side passage that engineers planned for and trained around extensively. The crew knows it is coming. Mission Control knows exactly when it starts and when it ends. There are protocols, there are procedures, there are contingency plans for the scenarios that have been anticipated. What cannot be planned for, what sits in the space beyond the edge of the known failure mode catalogue, is what happens if the communication blackout coincides with something that was not anticipated. Something invisible, something that does not announce itself with alarms or sensor readings, something that was happening in space long before Artemis II launched and will continue happening long after the mission ends, completely indifferent to the existence of the spacecraft or the 4 people inside it. The Sun has been building toward its peak activity for years. Solar Cycle 25 is approaching maximum, and what that means for 4 astronauts behind the Moon, beyond the reach of any warning system on Earth, is the kind of scenario that belongs in the next part of this conversation. Because the heat shield cracked, the lifeboat does not exist, the Moon will get in the way, and the Sun has been doing something that almost killed Apollo astronauts in August of 1972, and came within 45 days of catching a crew in exactly the wrong place at exactly the wrong time. Part 3. Deep Space Trap. Earth disappears. For approximately 45 minutes during the Artemis II mission, the 4 astronauts will pass behind the Moon, not near it, not around it, behind it. The Moon, a sphere 3,474 kilometers in diameter, with no atmosphere to bend radio signals around its edge, with no ionosphere to scatter electromagnetic waves, with nothing between its surface and the hard vacuum of space, except the occasional wisp of what scientists generously call a lunar exosphere, will place itself directly between the crew and every antenna, every tracking station, every flight controller, every person on Earth who is monitoring the mission. The radio waves that carry telemetry data and voice communication travel in straight lines at the speed of light, 300,000 kilometers per second, perfectly straight and completely unable to negotiate with a planetary body that happens to be in the way. For 45 minutes, the crew of Artemis II will be, in the most literal electromagnetic sense of the phrase, unreachable, not hard to reach, not difficult to reach, unreachable. The distinction matters because difficult implies that sufficient effort or technology could bridge the gap. Unreachable means the physics simply does not permit it. You could point every radio telescope on Earth at the spacecraft during the farside passage and receive nothing. You could transmit on every frequency in the electromagnetic spectrum simultaneously, and the crew would hear nothing. The moon is in the way, and the moon is not negotiable. Only 27 humans have ever experienced what that actually feels like from the inside. All of them flew on Apollo missions during the late 1960s and early 1970s in a compressed window of human history that has not been repeated since. Their descriptions of the blackout moment, the specific moment when Earth disappears behind the lunar limb, when the constant background chatter of mission control that has been present since launch suddenly gives way to complete silence, are remarkably consistent in their emotional register across the different missions and different crews. It is not fear, exactly. Fear has an object. Fear points at something. What Apollo astronauts describe is something more fundamental than fear, and something harder to name. It is the recognition of a kind of isolation that has no terrestrial equivalent and no adequate language in any vocabulary built by people who have never left the planet. You're not merely far from home. Distance alone does not capture it. You're in a location where home cannot perceive you, and you cannot perceive home, and the relationship between you and the rest of your species has been physically interrupted in a way that no other human experience replicates. The only things that exist in the perceptual universe for 45 minutes are the moon filling one window, the stars filling every other direction, and the four of you in a capsule the size of a large SUV. Michael Collins, orbiting above the moon in the Apollo 11 command module while Armstrong and Aldrin were on the surface, described it later as the most profound solitude he had ever experienced, and he was separated from the nearest humans by only a few hundred kilometers. The Artemis II crew will have 384,000 kilometers of empty space between themselves and the nearest other human being, with the moon blocking the view. But I want to be careful here, because the psychological dimension of the far side blackout, while genuinely interesting and worth sitting with, is not the operational problem. The human experience of isolation is compelling. The operational reality of 45 minutes of total communication blackout during a crewed mission with no rescue capability and a heat shield of uncertain behavior is a different category of concern entirely. The operational problem is this. During those 45 minutes, the crew of Artemis II will not be resting. They will not be floating peacefully in the spacecraft, watching stars through the windows and contemplating the human condition. They will be working. The far side passage is not a pause in the mission. It is a continuation of it, with all the same operational demands and all the same system monitoring requirements, now occurring in a context where the collaborative support structure that makes mission control valuable has been removed from the equation. Navigation assessments may occur during this window. System checks continue on schedule regardless of communication status. Potential burn preparations require crew attention, and if anything goes wrong during those 45 minutes, any anomaly anywhere in the spacecraft, any system alert, any unexpected reading in the propulsion data, or the power systems, or the life support telemetry, mission control will not know about it in real time. They will find out approximately 45 minutes later when the spacecraft emerges from behind the lunar limb and the telemetry link re-establishes. Whatever was happening will have been happening, undetected from the outside for the full duration of the blackout. 45 minutes is an enormous amount of time for a spacecraft to be experiencing an undetected problem. To understand exactly how enormous, it helps to put it in the context of the most famous emergency in human spaceflight history. The explosion that crippled Apollo 13's service module occurred at 55 hours and 54 minutes into the mission. The crew heard a bang. They felt the spacecraft shudder. Alarms activated, and within seconds, not minutes, seconds, Jim Lovell, Jack Swigert, and Fred Hayes were communicating the situation to Mission Control. Houston, "We've had a problem." The line is famous, and what makes it significant beyond its historical weight is the speed of it. The crew knew something catastrophic had occurred, and they were talking to Houston about it within moments of it happening. Mission Control had the telemetry. They could see the oxygen pressure dropping in real time. They could see the power systems degrading. They could watch the data and begin working the problem collaboratively with the crew before the full scope of the emergency had even finished developing. That collaborative real-time loop, the crew's direct sensory experience of the spacecraft combined with Mission Control's access to full telemetry data and the entire technical resources of NASA's engineering infrastructure, was not incidental to the survival of the Apollo 13 crew. It was central to it. Every decision that saved those 3 people was made in a context of continuous information flow between the spacecraft and the ground. The improvised carbon dioxide scrubber, the power-down sequence, the trajectory burns. All of it required the ground and the crew to be in constant contact, sharing data, building a picture of the situation together, and responding to how that picture changed in real time. On Artemis II, during the Farside passage, that loop does not exist. The crew is operationally autonomous in a way that has no peacetime equivalent for any other profession on Earth. Whatever happens, happens. Whatever decision gets made by 4 people in a capsule with the training they brought with them, the data their own instruments can provide, and nothing else. No additional engineering expertise available, no outside perspective on the sensor readings, no ground team running parallel analysis on the same data set. Just the 4 of them, and whatever the spacecraft is doing. The crew is trained for this. This is not a criticism of their preparation. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen are among the most capable and comprehensively trained human beings on Earth. Their selection and preparation for precisely this kind of autonomous operational challenge represents years of work. They have trained for communication blackout scenarios specifically. They know it is coming. They have procedures. They have contingencies. But there is a difference between capability and omniscience that no amount of training closes. You can be perfectly prepared and still encounter a failure mode that your simulations did not specifically include, in a combination of system states that did not appear in your training scenarios, in an environmental condition that no one modelled in advance with sufficient precision. And it is exactly that space, the space between the anticipated and the unanticipated, that the Farside passage makes dangerous in a way that no other phase of the mission does. Because in every other phase, when the unanticipated appears, Mission Control is in the loop within seconds. Behind the moon, it is in the loop 45 minutes later. This is the precise moment in the conversation to introduce what was happening in space in August of 1972, because it is both historically important and immediately relevant to the situation 4 astronauts find themselves in right now. And because it almost did not remain historical, it almost became something else entirely. The Sun is a variable star. That sounds like jargon, but it means something specific and consequential. The Sun does not produce energy at a constant rate. It breathes, in a sense, on an approximately 11-year cycle of activity. At the bottom of the cycle, solar minimum, the Sun's surface is relatively quiet. Sunspots are few. Energetic outbursts are infrequent. At the peak of the cycle, solar maximum, the Sun's magnetic field is in its most tangled, most stressed, most energetically active configuration. Sunspots multiply, solar flares erupt, and most importantly for anyone operating outside the protection of Earth's magnetosphere, coronal mass ejections, massive eruptions of magnetized plasma and high-energy particles, occur with increased frequency and intensity. The period from August 4th through 10th of 1972 produced what solar physicists now consider one of the most powerful and rapidly evolving sequences of solar particle events ever recorded during the space age. A coronal mass ejection of extraordinary intensity sent a wave of high-energy protons streaming through the inner solar system. These were not the relatively gentle particle events that the standard solar monitoring infrastructure was calibrated to flag as elevated but manageable. These were protons accelerated to a significant fraction of the speed of light, carrying enough energy to penetrate the aluminum walls of a spacecraft and deposit meaningful radiation doses in biological tissue within a time window of hours. The estimated radiation dose that an Apollo crew would have received if they had been in transit between Earth and the Moon during the peak of that event ranges, depending on the analysis and the assumptions about spacecraft shielding geometry, from acute radiation sickness levels to doses that some analyses describe as potentially lethal for at least some crew members without intervention. The shielding available on an Apollo command module, primarily the aluminum structure of the hull itself, was designed to attenuate routine cosmic ray exposure and moderate solar particle events. It was not designed to stop an event of August 1972's magnitude. Nothing that could realistically fly to the Moon in that era was. The event happened between Apollo 16 and Apollo 17. Apollo 16 splashed down in April of 1972. Apollo 17 launched in December of 1972. The solar storm hit in August. The gap between an active Apollo crew and a solar particle event capable of killing them was 45 days. Not a comfortable margin, not an engineering margin, a timing coincidence. The fact that no Apollo crew was in cislunar space during that event is not a result of careful solar weather planning or sophisticated radiation forecasting. It is the result of the mission schedule happening to land on the right side of a random natural event. Artemis II is launching near the peak of solar cycle 25. The timing is not a choice. The mission schedule is driven by 100 factors that have nothing to do with the solar cycle, and solar maximum is a multi-year period, not a single moment, so there is no clean way to schedule around it. The mission is flying when it is flying, and the sun is doing what the sun is doing, and those two facts exist in the same physical reality simultaneously. The crew has access to a designated radiation shelter inside the Orion capsule. It is not a separate room or a heavily shielded compartment in the way that science fiction might depict a radiation shelter. It is a defined area within the capsule where the crew can position themselves to maximize the amount of material between themselves and the incoming particle flux, using the spacecraft's own structure, the water and food supplies, the equipment stowage, everything available as additional shielding. It provides meaningful dose reduction compared to being in an unoptimized position in the capsule. It is not a guarantee, it is a mitigation. Mission Control monitors solar activity continuously through a network of space weather observatories. The NOAA Space Weather Prediction Center tracks solar conditions in real time and can issue warnings when elevated particle flux is detected. If a solar particle event begins while the Artemis II crew is on the near side of the Moon, while communication is maintained, Mission Control can warn them. The crew can move to the shelter position. They can reduce their exposure and manage the dose they receive over the duration of the event. But here is the scenario that sits at the intersection of two separate vulnerabilities and produces something more concerning than either one individually. If a major solar particle event begins while the crew is behind the Moon, if the onset of the storm falls inside the 45-minute farside blackout window, Mission Control cannot warn them. The warning system, the monitoring infrastructure, the real-time solar weather tracking, all of it becomes irrelevant because the communication link is down. The information exists on Earth. The warning would be sent immediately if the link were active, and the crew has no way to receive it. The crew's own instruments can detect the onset of increased energetic particle flux. The spacecraft carries radiation monitors that provide local readings of the particle environment. But here is the physics that makes this genuinely uncomfortable. The most dangerous solar particle events, the ones with the highest energy protons, the ones capable of delivering serious biological doses quickly, have a characteristic temporal structure. The highest energy particles arrive first, moving at the highest velocities as a relatively brief precursor to the main body of the particle wave. This precursor is the warning. If you see it and recognize it quickly, you have some lead time before the bulk of the dose arrives. That lead time is measured in minutes, not hours, minutes. And if the crew is in the middle of a navigation burn, or troubleshooting an unrelated system anomaly, or dealing with any of the other operational demands of the Farside passage, at the moment the radiation monitors start registering anomalous readings. If no one is watching that specific display at that specific moment, the response time compresses. The precursor passes, the main event arrives, and the shelter position that would have meaningfully reduced the dose becomes less useful with every minute of additional exposure that occurred before the crew got there. Radiation is the most philosophically unsettling hazard of the space environment, and I want to take a moment to explain why, because it is not just about the biological danger. It is about the complete mismatch between the nature of the threat and the sensory equipment that human beings evolved to detect threats. Every physical danger that shaped human evolution over millions of years announced itself through the senses. Fire is visible and hot. A predator makes noise and movement. A fall has a sensation. Even chemical hazards in the natural environment tend to have smell or taste as warning signals. Human biology is exquisitely tuned to detect and respond to threats that interact with the physical world in ways that produce sensory information. Ionizing radiation produces no sensory information whatsoever at the doses relevant to a solar particle event. You cannot see it. You cannot hear it. You cannot feel it. You cannot smell it. There is no sensation of warmth, no tingling, no proprioceptive signal that anything is happening. The high-energy protons from a solar particle event pass through the spacecraft walls, through the crew's bodies, through everything in the spacecraft, at a significant fraction of the speed of light, depositing energy in biological tissue through ionization interactions that are completely below the threshold of human sensory detection. The first indication that something significant has happened might be nausea, hours later, or fatigue, or the beginning of symptoms that will not fully manifest for days. The crew cannot look out the window and assess the radiation environment. They cannot develop intuition about it from experience the way a sailor develops intuition about weather. It is invisible, it is silent, it is physically indifferent to the fact that there are 4 human beings trying to manage it, and the only interface between the crew and any knowledge of what the radiation environment is doing is the readout on an instrument display that requires someone to be actively looking at it at the right moment. Now layer on top of all of this a navigation problem, because the communication blackout, the radiation vulnerability, and the navigation challenge of Artemis II are not 3 separate issues sitting in separate compartments of the mission risk profile. They are connected through the spacecraft's electronic systems, and understanding the connection requires understanding exactly how unforgiving the geometry of lunar return re-entry actually is. At 25,000 miles per hour, 40,000 kilometers per hour, the Orion spacecraft approaching Earth for re-entry must enter the atmosphere within an angle of between 5.5 and 7 degrees relative to the local horizon. Let me build that picture carefully, because the number sounds small until you understand what it means physically at that speed and distance. Shallower than 5.5 degrees, and the spacecraft does not enter the atmosphere in any meaningful sense. At 25,000 miles per hour, a shallow trajectory angle causes the spacecraft to skip off the upper atmosphere the way a flat stone skips across the surface of a pond. The atmospheric density at the altitude where a 5-degree entry would interact with it is so low that instead of decelerating the capsule, it simply deflects it. The spacecraft bounces back into space on a modified trajectory. At that speed, the energy involved in the skip disperses the trajectory in ways that put the spacecraft somewhere other than the planned recovery zone, potentially in the wrong ocean, potentially in a trajectory that does not return to Earth at all within a useful time frame, with a crew running out of consumables. Steeper than 7 degrees, and the atmosphere is dense enough at the entry point to create aerodynamic loads and heating rates that exceed what the structure of the spacecraft was designed to survive. The heat shield, the one that already spooled, encounters a thermal environment more extreme than its design envelope. The aerodynamic forces on the capsule at the steeper angle exceed the structural margins. The spacecraft does not make it through re-entry intact. 1.5 degrees. Between those two outcomes there is a window of 1.5 degrees. I want to give you a physical reference for what 1.5 degrees actually looks like, because it is genuinely difficult to intuit. Extend your arm fully in front of you and look at your little finger. The apparent width of your little finger at arm's length subtends approximately 1 degree of visual angle for a typical adult. Your entry window for Artemis II is 1.5 times the apparent width of your little finger held at arm's length. And you're trying to thread that window from approximately 250,000 miles away, travelling at 10 times the speed of a rifle bullet, with a trajectory that has been accumulating any navigation errors that occurred during the transit. Under nominal conditions, the guidance computer manages this. The Orion spacecraft's guidance, navigation, and control system is considerably more sophisticated than anything that flew on Apollo. It processes sensor data continuously, calculates the spacecraft's current state vector, its position, velocity, and attitude, and makes real-time corrections to ensure that the re-entry trajectory stays within the entry corridor. It is good at this. The system was designed specifically for the narrow entry corridor of lunar return, and the algorithms that run it represent decades of accumulated expertise in spacecraft guidance. But the guidance computer is an electronic system. Every electronic system operating in the space environment is exposed to ionizing radiation, and here is where the radiation vulnerability and the navigation challenge connect directly. High-energy protons from the solar environment, the same particles that pose a biological risk to the crew, also pose a risk to electronics. When a high-energy particle passes through a semiconductor memory chip, it can deposit enough charge in a single memory cell to spontaneously flip the bits stored there from a 0 to a 1, or from a 1 to a 0. Engineers call these events single-event upsets, or more colloquially, bit flips. Most bit flips in spacecraft computers are caught. Modern radiation-hardened electronics use error detection and correction codes, additional redundant bits that allow the computer to identify when a bit has flipped and correct it without losing data or corrupting a calculation. The system works well for the vast majority of events, but bit flips in critical navigation calculations, particularly if they occur in the specific memory locations holding the values that define the entry corridor parameters, or in the real-time state vector calculations that feed the guidance algorithm, can potentially translate into trajectory decisions with physical consequences. A guidance computer that believes it is targeting a 6-degree entry angle when it's actually targeting a 4.5-degree entry angle will fly a trajectory that skips off the atmosphere. The backup to a failed or corrupted guidance computer is, at its core, the same system that the Apollo crews used and that navigators used for centuries before the space age: star navigation. The crew can use a sextant-type optical device to measure the angular positions of known stars relative to the spacecraft's attitude and the Earth's limb, calculate the spacecraft's precise orientation and trajectory from those measurements, and use that calculation to correct the re-entry targeting. The mathematics behind it are sound. The technique works. It worked on Apollo, the crews trained in it, used it as a backup and validated that it could substitute for the primary guidance system under failure conditions. But it requires time. It requires the crew to be physically and cognitively in a state where they can perform precise optical measurements and mathematical calculations. It requires that whatever failure condition necessitated the backup, whether radiation-induced corruption of the guidance computer, a software anomaly, or a hardware failure, has not also affected the crew's ability to execute the technique. If the failure event that degraded the guidance computer was a severe solar particle event, and the crew has been receiving radiation exposure during the same period, the question of their cognitive status at the moment they need to perform emergency manual navigation becomes a real operational question, not an abstract one. In the most extreme failure scenario imaginable, guidance computer corrupted, crew managing radiation exposure, communication blackout still in effect, re-entry window approaching, the most sophisticated crewed spacecraft ever constructed, falls back to a human being with an optical instrument measuring the angle between a star and the Earth's horizon, doing the same mathematics that maritime navigators did with sextants on wooden ships crossing unknown oceans. That is not a weakness of Artemis. That is not a design failure. That is the physics of the problem, irreducible and non-negotiable. Under conditions of extreme system failure, complexity collapses. The layers of redundancy and automation and sophisticated technology peel back one by one, and you find underneath them the same irreducible challenge that has always been at the center of navigation: a human being, an instrument, and the geometry of the sky. The stars do not change, the mathematics does not change, the margin for error does not change. What changes is everything surrounding those constants: the speed, the altitude, the precision required, the physiological state of the person doing the calculation, the time available, the consequences of being wrong by half a degree. And this is where the cumulative nature of Artemis II's risk profile becomes most visible. The heat shield is uncertain at its thermal limits. The service module is a single consolidated dependency. The communication blackout removes the collaborative safety net for 45 minutes. The solar maximum raises the radiation environment above nominal. The radiation environment threatens both the crew biologically and the guidance electronics operationally, and the guidance electronics, if compromised, push the navigation challenge back onto the crew at the moment the mission demands the most precise targeting in all of human spaceflight. These are not independent risks. They are connected risks because they share a common substrate, the spacecraft and the people inside it, and a degradation of that substrate by any one of them affects the crew's and the spacecraft's ability to manage all the others. This is what engineers mean when they talk about risk stacking, not just the accumulation of individual probabilities, but the coupling of failure modes through shared systems and shared human capacity. The scenario where everything goes wrong simultaneously is not just the sum of the individual failure probabilities. It is a different category of scenario, because in the coupled system, failures create conditions that make subsequent failures more likely. There is one more category of risk on this mission that operates differently from all the ones discussed so far. The communication blackout ends. The radiation storm, if it comes, eventually passes. The re-entry corridor is threaded or it is not. But somewhere in the cislunar environment, spread through the volume of space between Earth and the Moon, there are objects travelling at velocities that no amount of planning or execution or crew skill can address. They cannot be detected in advance. They cannot be warned against. They cannot be navigated around. And the only thing standing between the crew and their impact is a calculation about how much shielding mass the spacecraft can carry without becoming too heavy to launch. The next part of this story is about what it means to accept a risk you have absolutely no control over, and about the 3 parachutes at the end of the mission that everyone assumes will work, right up until the moment they discover whether they do. Part 4. Low probability events that end everything. Space is not empty. That statement sounds obvious when you say it out loud, but the mental image most people carry of the space between Earth and the Moon is essentially one of pure, featureless void. Darkness interrupted by the occasional dramatic object. The reality is considerably more crowded and considerably more dangerous in a way that operates below the threshold of human perception and entirely outside the reach of human response. The cislunar environment, the volume of space between Earth and the Moon, is an active debris field. Not in the cinematic sense of visible rocks tumbling dramatically through darkness, the kind of thing that makes good visual effects in science fiction films. In the physical sense of a volume of space populated by particles ranging from microns to meters in diameter, distributed across an enormous volume, moving in trajectories that are the accumulated result of billions of years of solar system dynamics. Natural micrometeoroids shed from comets and asteroids, fragments of larger objects broken apart by previous collisions, dust particles so small they're essentially invisible and so fast they carry energy that makes their size irrelevant. The impact velocities for objects in cislunar space range from roughly 3 kilometers per second on the low end to approximately 70 kilometers per second for debris on the most energetically unfavorable trajectories. To make those numbers mean something, a 9mm pistol bullet, which is approximately the fastest projectile most people have any intuitive reference for, leaves the muzzle at roughly 370 meters per second. The lower bound of micrometeorite impact velocity in space is 8 times faster than that bullet. The upper bound is nearly 200 times faster. You're not dealing with faster bullets. You're dealing with a different physical category of impact event entirely. At those velocities, mass stops behaving the way it does in any impact scenario within ordinary human experience. The relationship between mass and kinetic energy is not linear. Kinetic energy scales with the square of velocity, which means doubling the speed of an object quadruples its energy. And the velocities involved in cislunar debris impacts are so far beyond anything in terrestrial experience that the mass of the impactor becomes almost secondary to its speed. A particle the size of a single grain of sand, arriving at 40 kilometers per second, carries kinetic energy roughly comparable to a rifle round. A particle the size of a small marble at the same velocity delivers energy comparable to a hand grenade. These are not metaphors chosen for dramatic effect. They are the actual physics of what happens when small, fast objects meet spacecraft hulls. The Orion capsule is shielded against micrometeorite impacts. Multiple layers of aluminum and other materials are incorporated into the hull design specifically to absorb and disperse the energy of particle strikes. A Whipple shield design, named after the astronomer Fred Whipple, who first proposed the concept in 1947, where a thin outer bumper plate vaporizes or fragments the incoming particle and spreads its energy across a wider area before it can reach the primary pressure hull. The shielding was designed to protect against the statistical distribution of most likely impact events, optimized against the mass and velocity profile that represents the overwhelming bulk of the cislunar debris population. It works well for that population. It was not designed to stop everything. It cannot stop everything. Designing a spacecraft hull to stop everything, the cislunar environment could theoretically deliver, would require so much shielding mass that the spacecraft would be too heavy to launch. This is the fundamental, non-negotiable trade that every spacecraft designer makes. Shielding adds mass. Mass requires more thrust to lift. More thrust requires more fuel. More fuel adds more mass, which requires more thrust, which requires more fuel, in a cycle that quickly makes the spacecraft impractical. At some point in the optimization, you accept the residual risk of the impacts you cannot realistically shield against, because the alternative is not flying at all. A micropuncture, a pinhole breach of the pressure hull from a small high-velocity particle that the shielding did not fully stop, produces a slow depressurization. The pressure differential between the cabin interior, which is maintained at roughly sea-level atmospheric pressure, and the vacuum outside, which is as close to absolute zero pressure as anything in the natural universe, drives air through the breach at a rate governed by the size of the hole. A very small hole leaks slowly. Slowly enough, potentially, that the crew's instrumentation detects the pressure drop before it becomes physiologically significant. The Orion capsule has sensitive pressure monitoring. The crew is trained for hull breach scenarios. A slow leak is manageable, at least initially, at least if it is detected promptly, and if the source can be identified and addressed. A larger impact changes the equation in ways that do not scale linearly. A breach the diameter of a pencil depressurizes the cabin dramatically faster than a pinhole. The response time for the crew compresses from potentially minutes to potentially seconds. And a significant impact, one that penetrates not just the outer shielding layers and the pressure hull, but the underlying structural members of the capsule, introduces failure modes for which there is no response protocol because there is no response to catastrophic structural failure of a pressure vessel in the cislunar environment. There is no patch. There is no repair procedure. There is no hull breach scenario in the training manual that addresses the loss of structural integrity of the pressure vessel itself, because that scenario does not have a survivable outcome. The probability of a micrometeorite strike during the Artemis II mission is low. The probability of a penetrating strike is lower still. The probability of a mission-ending strike is lower than that. All of those statements are accurate. They are also, in a very specific sense, beside the point. The universe does not consult probability tables before deciding where a given particle is on a given day. The probability assessment tells you what to expect across a large number of missions. It tells you approximately nothing about what happens on this specific mission to these specific 4 people during this specific transit. Low probability is a statement about a population of events. The crew of Artemis II is not a population. They are 4 individuals, and for them, any given impact either happens or it does not, and the probability that preceded it is irrelevant once the particle is in flight. This is the fundamental honesty that Artemis II demands, both from the people making the decisions and from the people observing them. Low probability is not the same as impossible, and across a mission profile with this many independent low probability risk elements, the heat shield, the service module dependency, the communication blackout, the radiation environment, the navigation corridor, and now the debris field, the cumulative probability of something unexpected occurring rises with each additional element simply because the number of opportunities for the unexpected is large. But if you're looking for the single moment in the Artemis II mission where the convergence of failure modes is most uncomfortable to contemplate, it is not in the transit phase. It is not behind the moon. It is not during the solar maximum exposure window. It is at the very end, after everything else, after the heat shield has done its job, after the entry corridor has been threaded at 25,000 miles per hour, after the crew has survived everything the cislunar environment and the deep space radiation field delivered. The moment of maximum vulnerability on Artemis II is when 3 parachutes are supposed to open above the Pacific Ocean. The Orion capsule does not glide to a landing. It does not have wings or a runway or a controlled aerodynamic approach. It falls. After re-entry, after the heat shield has shed the thermal energy of atmospheric entry, and the capsule has decelerated from orbital velocity to something closer to freefall terminal velocity at low altitude, the parachute system deploys in a carefully sequenced cascade. Drogue shoots first to stabilize the capsule's attitude and begin the deceleration. Then the 3 main parachutes, large enough that their combined canopy area covers roughly the footprint of a small office building, slowing the descent to a splashdown speed that the capsule structure and the crew can survive. 2 of the 3 main parachutes must function. That is the threshold. 1 failure is within the system's design tolerance. The 2 remaining parachutes can still bring the capsule to a survivable splashdown velocity. 2 failures are not tolerable. The descent rate on a single parachute exceeds what the capsule's structure and the crew's bodies can withstand at splashdown. And here is the thing about the parachute system that connects it back to everything discussed in this video. The deployment conditions, the altitude, the velocity, the capsule's pitch angle, the aerodynamic loads it is experiencing at the moment of deployment are not independent of the decisions made earlier in the mission. The trajectory modification that NASA implemented to reduce the heat shield's thermal exposure changes the capsule's energy state at re-entry. A different energy state at re-entry means a different velocity profile through the atmosphere. A different velocity profile means the capsule arrives at parachute deployment altitude in a slightly different condition than the nominal mission design assumed. The parachutes were tested and validated against the nominal conditions. The actual conditions will be the modified ones. None of this means the parachutes will fail. It means the conditions they are deploying into are not identical to the conditions they were primarily validated against, because the conditions upstream were changed to manage a different risk. The risks are coupled. Changing one changes the environment faced by the others, and then there is the scenario that does not involve catastrophic failure at all. No explosion, no micrometeorite, no parachute malfunction, just a burn that delivers slightly less than nominal thrust. A trajectory that diverges from the planned path by a fraction of a degree, so small that the initial telemetry does not flag it as critical, accumulating over distance into a divergence that becomes significant only when it is too late to correct it, with the propulsion budget remaining. If the service module's main engine underperforms during the critical return burn, not fails completely, which would trigger immediate emergency protocols, but delivers 94 or 95% of nominal thrust over a burn duration slightly longer than planned, the trajectory geometry shifts. The spacecraft arrives at the Moon's gravitational sphere of influence on a slightly different vector than intended, and instead of the free return geometry curving it back toward Earth, the Moon's gravity captures it. The spacecraft enters an elliptical orbit around the Moon. It is not falling toward Earth, it is falling around the Moon in a closed orbit, going nowhere. The crew would know immediately. The telemetry would be unambiguous. Communication with mission control would be intact. This scenario does not involve the far side blackout. Mission control and the crew would have a complete and shared picture of what had happened and what it meant. They would work the problem together with every resource NASA's engineering infrastructure could bring to bear, because that is what NASA does, and those are the people involved. And at the end of that process, they would arrive at number, a delta V figure, the change in velocity required to break out of the lunar capture orbit and set a course for Earth, and they would compare that number to the propellant remaining in the service module after the underperforming burn. And if the numbers did not match, if the physics of the situation required more energy than the spacecraft had remaining to provide, the conversation would reach a point where the engineering options were exhausted. Earth would be visible through the capsule windows. A blue-white sphere, roughly the size of a marble held at arm's length, approximately 384,000 kilometers away. A radio signal crosses that distance in 1.3 seconds. The crew could talk to their families, they could talk to mission control, they could see with their own eyes the planet they came from and the planet they were trying to return to. And the orbital mechanics would be indifferent to all of it. Proximity does not equal accessibility in space. You cannot negotiate with a gravitational field. You cannot improvise your way out of a propellant deficit. Earth would be right there, visible and radio reachable and completely, physically unreachable, and the gap between those two facts would be the whole story of what it means to be a human being in deep space with an insufficient delta V budget. That scenario, quiet, slow, technically understood, survivable in its initiation, and unsurvivable in its conclusion, is the one that most cleanly illustrates what Artemis II actually accepted. Not the fire, not the impact, the math. Part 5. What we are really accepting. In 1969, when Apollo 11 returned from the lunar surface and splashed down in the Pacific Ocean, 3 of the most celebrated human beings on the planet were immediately placed in a modified Airstream trailer and told they could not leave. For 21 days, Neil Armstrong, Buzz Aldrin, and Michael Collins lived in a converted mobile quarantine facility, a sealed, pressurized trailer with small windows and limited space, docked to the side of the USS Hornet recovery ship, while scientists monitored them for any sign that they had brought something back with them that Earth was not prepared for. They had just done something no human being had ever done. They had walked on another world. They had touched its surface, breathed recycled air above it, and returned. And the first thing the institution that sent them there did was lock them in a trailer for 3 weeks, just in case. The quarantine protocol was not based on evidence. Nobody had found lunar microorganisms. Nobody had a specific threat model for what a lunar pathogen would look like, how it would transmit, or what it would do to human biology. The protocol was based on something more fundamental than evidence. It was based on the principle that the probability of something harmful existing in the lunar environment was not precisely 0, and that the consequences of being wrong were significant enough to justify an expensive, logistically complicated precaution against a threat that almost certainly did not exist. That is a very specific kind of thinking. It is not the thinking of someone who has modelled the risk and found it acceptable. It is the thinking of someone who has looked at the edge of the unknown and decided that the cost of being cautious is lower than the cost of being wrong, in a domain where being wrong cannot be undone. It is, in a certain sense, the opposite of the bounded uncertainty philosophy that defines Artemis II. Apollo quarantined the crew not because the math said to, but because the math could not be trusted in a situation with no precedent and potentially catastrophic downside. NASA ended the lunar quarantine requirement after Apollo 14. 3 missions had gone to the moon. 6 astronauts had walked on the surface. Nothing concerning had been found. The probability assessment shifted from unknowable to effectively negligible, and the precaution was removed. This is how institutional risk assessment is supposed to work over time. You begin with a wide margin of uncertainty. Experience narrows it. The margin shrinks. The precaution relaxes proportionally. You learn from each mission. You carry better information into the next one. The system gets safer as the knowledge base expands. But here is the thing about that process that matters for understanding Artemis II. It works beautifully when the risks you're accumulating experience with are the same risks you will face on subsequent missions. When the threat model is stable, when the domain of the unknown does not expand faster than the domain of the known. The lunar quarantine is a good example of the process working correctly. Repeated missions to the same environment, consistent absence of the hypothesized threat, rational relaxation of the precaution. The risk profile of Artemis II is not like that. The heat shield spallation is not a risk that accumulated experience has characterized into predictability. It is a risk that appeared during the only test flight and was managed through trajectory modification rather than resolved through redesign. The knowledge base did not expand to close the uncertainty. The uncertainty was bounded, given a defined shape, assigned a probability, and then accepted. Those are different things, and as Artemis progresses from flyby to surface landing to long-duration stay, the risks do not remain static while experience accumulates. They evolve, they compound. New unknowns appear faster than old ones are resolved. The biological dimension of this is worth staying with for a moment, because it extends in 2 directions that both matter and that most coverage of Artemis does not spend much time with. The inbound direction, whether the lunar environment could contain anything that might affect the crew, is the one the Apollo quarantine addressed. For Artemis II, which does not land on the surface and does not collect samples, the inbound biological risk is genuinely minimal. The crew's exposure to the lunar environment is indirect and limited. The outbound direction is more interesting and more consequential for the program's long-term trajectory. Planetary protection, the formal scientific discipline concerned with preventing Earth organisms from contaminating other worlds in ways that would compromise future scientific study of those worlds, has requirements that vary by destination. Mars gets the strictest protocols because Mars is considered a plausible candidate for harbouring microbial life, and because contaminating it with Earth bacteria, before we can determine whether life exists, there would be a scientific catastrophe. The Moon gets less strict protocols because the lunar surface environment, bathed in ultraviolet radiation, exposed to the solar wind, with no liquid water and temperatures ranging from over 100 degrees Celsius in sunlight to below negative 170 degrees Celsius in shadow, is considered relatively inhospitable to Earth biology. Relatively inhospitable is not impossible. Certain Earth microorganisms, the extremophiles, the organisms that thrive in volcanic vents and hypersaline lakes, and the irradiated cores of nuclear reactors, have demonstrated a capacity to survive in conditions that intuition would suggest are incompatible with life. Whether any Earth organism could survive on the lunar surface long enough to establish a presence is genuinely uncertain. Whether it matters for a flyby mission like Artemis II is probably not. The crew does not go to the surface, and the spacecraft's controlled hardware is not being deposited on the Moon. But as Artemis moves towards surface operations, the outbound contamination question accumulates relevance in a way that will eventually require the same kind of careful, precedent-establishing decisions that the Apollo quarantine represented. The unknowns in human deep space travel are not purely mechanical. They are biological, psychological, physiological, and in some ways that are harder to categorize, existential. The long-term effects of radiation exposure on the human body over mission durations measured in months rather than days. The psychological effects of genuine isolation, not the simulated isolation of training facilities, but the real isolation of being in an environment where Earth is not just far away, but in some phases of the mission, electromagnetically unreachable. The physiological effects of microgravity on bone density, cardiovascular function, and immune response over the durations required for Mars transit. Artemis II is a short mission by the standards of what follows it, but it is establishing precedents in risk philosophy, in mission architecture, in what acceptable means, that will carry forward into missions where the biological and psychological stakes are considerably higher. The far side of the Moon sits in a peculiar position in the human imagination, and it is worth examining that position carefully because it illustrates something important about the relationship between knowledge and experience that runs through this entire story. The far side is not unknown. That is worth stating clearly, because the phrase dark side of the Moon, which is technically inaccurate but culturally pervasive, implies a mystery that does not scientifically exist. The far side receives as much sunlight as the near side, averaged over a lunar month. It has been comprehensively mapped. The Lunar Reconnaissance Orbiter has photographed every square kilometre of it, at resolution sufficient to identify features the size of a small car. Chang'e 4 landed on it in 2019 and has been operating there since. We know the far side's geology, older, more heavily cratered than the near side, with fewer of the large dark plains called Maria that give the near side its characteristic appearance. We know its gravity field, its crater size distribution, its mineralogical composition in broad strokes. In the scientific sense, the far side of the Moon is perhaps the most thoroughly characterized piece of territory in the solar system that no human being has physically visited, and none of that knowledge translates into the experience of being there. 27 humans have passed behind the Moon. 27 people across a small number of Apollo missions in a compressed window of history that ended in December 1972, have been in the only location accessible to human beings where Earth is not merely distant, but invisible. Where the electromagnetic connection to the entire rest of the human species, the continuous background hum of radio signals and telemetry, and voice communication that has been present every moment since launch, is physically interrupted and replaced by silence. Not the silence of a quiet room, the silence of a severed connection, the silence of a medium that carries no signal because the signal cannot reach it. Their accounts of the experience are remarkably consistent in certain ways and remarkably varied in others. The consistency is in the register. It is almost universally described as something that does not map onto prior experience. Not frightening in the way that fear of a specific danger is frightening. Not lonely in the way that ordinary loneliness is lonely. Something more fundamental, something that the existing vocabulary of human emotional experience was not quite built to describe, because the experience itself has no terrestrial equivalent, and the language evolved to describe terrestrial experiences. Michael Collins, orbiting above the lunar surface during Apollo 11, while Armstrong and Aldrin were below, wrote about the far side passage as the most complete isolation he had ever experienced. He was alone in a way that he found, somewhat to his own surprise, not oppressive but clarifying. The noise of the world, all the competing demands and communications and relationships that constitute ordinary human existence, was simply gone, not suppressed, gone. He described looking at the stars in a way that was different from looking at stars from Earth, and different again from looking at them from low Earth orbit, where the planet still fills a significant portion of the visual field. Behind the Moon, Earth was absent. The stars were everything, and the silence was absolute. The Artemis II crew will be the first humans to experience that in over 50 years. That generational gap matters, not because the physics of the far side passage has changed, it has not, but because the cultural and psychological context has changed enormously. The Apollo astronauts were products of a military aviation culture that valued emotional stoicism and operational focus above almost everything else. Their descriptions of the far side experience, while consistent in noting its unusual quality, were characteristically understated. The Artemis crew will experience the same physics in a different psychological context, with different preparation, different expectations, and different tools for articulating what they find. What they will not have that is different is more time. 45 minutes. The same window every Apollo crew had. The same operational demands, system monitoring, navigation assessment, the ongoing work of keeping a spacecraft functioning in a genuinely hostile environment. The same complete absence of the ground support infrastructure that backs every other phase of the mission. The same irreducible reality. For 45 minutes they are alone in a way that the word alone was not really built to describe. It is possible, and I think it is worth saying this directly rather than hedging it, that this experience does something to a person that cannot be fully communicated afterward. That the direct physical experience of being in a location where home is not just far away, but electromagnetically absent, produces a recalibration of perspective that no amount of intellectual knowledge of the distances involved can replicate. The astronauts who flew Apollo describe something like this, consistently enough that it seems worth taking seriously rather than dismissing as sentiment. A shift in the relationship between self and planet. A recognition of scale that astronomy as an intellectual discipline does not deliver, but direct experience apparently does. An understanding, not conceptual but visceral, of what it means to be a biological organism operating outside the environment it evolved for. That recognition, felt rather than thought, known in the body rather than in the mind, connects to the deepest question this video has been building toward from the beginning. The question that the heat shield anomaly, and the launch abort paradox, and the communication blackout, and the radiation vulnerability, and the navigation corridor, and the micrometeorite risk, and the parachute finality, are all, in their different ways, circling. What exactly was accepted? Not the specific risks. Those have been catalogued. The heat shield spallation, the trajectory modification, the 1 in 30 crew loss probability, the 45-minute blackout, the solar maximum radiation environment, the cislunar debris field, the 1.5 degree entry corridor, the 2 of 3 parachute threshold. All of those are known. All of those were assessed. All of those were formally documented, institutionally accepted. What was accepted underneath all of those specific items is a condition, a fundamental condition of human existence in space that no engineering can eliminate and no risk assessment can reframe away. The condition is this, that the space between Earth and the Moon is an environment that was not built for human beings, does not accommodate human biology on its own terms, and will not make exceptions for human intentions or human courage or human engineering sophistication. The margins are real. The math is solid. The probability assessments represent the best available human knowledge. And none of that changes the physical fact that every kilometre away from Earth is a reduction in options and an increase in dependence on physics alone. The worst-case scenario for Artemis II, the one that should occupy the thoughtful observer more than any of the failure modes, is not the heat shield burning through. It is not the radiation storm during the blackout window. It is not the navigation error that produces lunar capture orbit. All of those are terrible outcomes. All of them sit within the probability space that was assessed and accepted. But they are not the worst case in the sense that matters most for the long arc of human spaceflight. The worst case is a successful mission. Here is why, and I want to be precise about this because it is easy to misread as cynicism when it is actually something more complicated. If Artemis II returns safely, if Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen splash down in the Pacific Ocean and climb out of that capsule having flown through everything described in this video and come back intact, something specific will have been demonstrated. Not that the mission was safe, that the mission was survivable, and those are not the same statement. Safe means the risks were within understood and controlled parameters. Survivable means the crew got through it. A mission can be survivable without being safe, and the history of spaceflight is full of missions that were survivable right up until the one that was not. The Space Shuttle flew 135 missions before Challenger and 113 missions before Columbia. It was declared fully operational after its fourth test flight. For more than 2 decades, the fact of its continued operation, mission after mission after mission, crews returning safely, the vehicle landing and being processed and launching again, was used, implicitly and sometimes explicitly, as evidence that its risks were understood and manageable. They were not. The O-ring erosion that destroyed Challenger was known about before the flight. The foam strike risk that destroyed Columbia was known about before the flight. The knowledge was present, the risk was assessed, the missions flew, and the missions that flew safely, the 132 successful missions between Challenger and Columbia, did not make the shuttle safer. They made the people making decisions about flying it more comfortable with the level of risk it carried. That is a different thing. That is normalization. And normalization is the process by which extreme uncertainty stops feeling extreme. Artemis II, if it succeeds, will begin the normalization of its specific risk profile. The spooled heat shield, managed through trajectory modification, will become a known quantity, not a solved problem, but an established precedent. The 1 in 30 crew loss probability will become the baseline from which subsequent missions are assessed. The 45-minute communication blackout will become routine operational territory, something the crews train for and manage, rather than an extraordinary condition that deserves sustained scrutiny. The service module's consolidated dependency architecture will be carried forward into missions with longer durations and higher operational demands. This is not inevitable. The normalization process can be interrupted by rigorous, sustained, institutionally supported attention to the distinction between survivable and safe. The lessons of Challenger and Columbia were precisely about the cost of failing to maintain that distinction. NASA knows this. The engineers who made the Artemis II risk assessments know this. The culture of modern spaceflight is in many ways more conscious of normalization risk than the shuttle-era culture was, but consciousness of a risk is not immunity to it. And the pressure to move forward, the schedule pressure, the budget pressure, the political pressure to demonstrate progress in human space exploration is as real for Artemis as it was for Shuttle. Maybe more real, given the international commitments and the commercial partnerships and the explicitly stated ambitions of the program. A successful Artemis II creates momentum. Momentum has its own logic, and the question of what gets carried forward in that momentum, what gets normalized, what gets accepted as baseline rather than interrogated as anomaly, is the question that will define not just Artemis II Iron 4, but the entire trajectory of human expansion beyond Earth. Because Artemis II is a proof of concept. It is the first data point in a series that is intended to extend eventually to the surface of Mars. The Moon is 384,000 kilometers away. Mars, at closest approach, is approximately 54 million kilometers away, roughly 140 times farther. A one-way transit to Mars takes somewhere between 7 and 9 months in current mission architectures. The radiation exposure over that transit, in the absence of Earth's magnetospheric protection, accumulates to levels that current shielding approaches cannot fully mitigate. The communication delay at Mars distance reaches up to 24 minutes one way, meaning that a question asked by a crew member in an emergency reaches Earth 24 minutes later, and the answer arrives 24 minutes after that. 48 minutes of round-trip communication latency in a situation where 45 minutes of one-way blackout is already considered operationally significant. There are no free return trajectories from Mars. The orbital mechanics of Earth-Mars transits do not offer the passive safety net that the lunar free return provides for Artemis. Once a Mars-bound crew commits to their trajectory, the physics of the situation commits them. There is no early return option. There is no passive mechanism that brings them home if propulsion fails. There is the ship, and the crew, and the 7 to 9 month transit, and whatever the destination looks like when they get there, and then the transit home. If Artemis II is where humanity is currently defining how much uncertainty it is willing to fly through on the way to the moon, then Mars is the question of how much uncertainty human beings are willing to live inside continuously for the better part of a year in each direction, with no rescue, no early return, no free return geometry, and a communication delay that makes real-time collaborative problem-solving with Earth physically impossible in pursuit of the answer to a question that might not have a satisfying answer. Space is indifferent to that question. The vacuum between planets does not care about the ambitions of the organisms traversing it. The radiation environment does not adjust itself for biological vulnerability. The physics of orbital mechanics does not make exceptions for engineering limitations or schedule pressures or the weight of human aspiration. Survival out there is probabilistic, not guaranteed, and every increment of distance from Earth is an increment of reduction in the options available when something goes wrong, and an increment of increase in dependence on physics alone, on the math working out, on the trajectory being correct, on the systems functioning within their design envelopes, on the crew being capable and healthy and functional at the moments when capability and health and function are most needed. The 4 astronauts out there right now know all of this, not abstractly, the way a person who has read about it knows it, but operationally, in the procedures they have memorized, the failure scenarios they have trained against, the risk assessments they have reviewed and signed off on and chosen to proceed with anyway. Reed Wiseman, Victor Glover, Christina Koch, Jeremy Hansen. They accepted not just the specific risks, but the condition underlying them. The fundamental condition of being human in a universe that was not arranged for human convenience. They are out there because the species they belong to has been asking a question for as long as it has been capable of asking questions. The question is simply, what is out there? And the answers that have come back from the places we have managed to reach, the moon, the planets, the space between them, have consistently been variations on the same theme. It is extraordinary. It is indifferent. It will kill you if you make a mistake, and possibly if you do not. And it is worth going anyway. Whether that calculation is correct is not a scientific question. It cannot be answered with data, or validated with a risk assessment, or resolved by a committee. It is the oldest question the species has, and Artemis II is the current generation's answer to it, imperfect, uncertain, bounded by the limits of what human engineering and human courage can currently support, and out there anyway. Every kilometre away from Earth is a reduction in options and an increase in dependence on physics alone. They are already out there.